Look at this terminal screen. This is a neural network generating original text, character by character, and it's running right now on a standard local machine. No internet connection, no API keys, and zero reliance on OpenAI's servers. In this video, we are going to write the complete Python code for a functional tiny GPT from scratch using PyTorch, walking through every line of the model's construction. You only need 3 things to follow along: your preferred IDE, a standard PyTorch installation, and a single small text file to serve as our training data. Building this miniature version demonstrates the transformer logic that serves as the basis for large-scale language modeling. Our neural network cannot read English letters. It only understands numbers. Step 1 is tokenization. We scan our text file to identify every unique character and assign each one a specific integer ID, creating a vocabulary map that our code can process. Next, we write a getBatch function. We can't dump the entire text file into the model at once without overloading our system memory. Instead, we sample small, constrained sequences to feed into the network iteratively. This graphic shows the core logic of our training data. For every input sequence labeled X, like "Hello friends, how are?", we create a corresponding target sequence labeled Y, shifted exactly 1 position into the future. "Friends, how are you?" A quick warning here. When you set your batch size and context length, double-check your variables. The most common error at this stage is accidentally asking the getBatch function to pull a sequence larger than the dataset itself, which will instantly crash your code. That deliberate off-by-1 offset allows the network to learn the mechanics of time and sequence prediction. Now we define our model by creating the tiny GPT class. We initialize 2 critical components here: token embeddings, which encode what a specific word is, and positional embeddings, which encode where that word sits within the current sequence. Look at the decoder stack in this architecture diagram. We map PyTorch code directly onto these boxes: masked multi-head attention, linear layers for the feed-forward network, and built-in layer normalization. Everything flows upward in a strict, consistent shape: batch, time, and embedding dimension. Stacking these specific layers together creates an engine that evaluates every single token against every other token in the sequence, allowing the model to isolate context and meaning over long stretches of text. With the architecture built, we set up the training loop. We instantiate our tiny GPT model and pair it with an optimizer, in this case PyTorch's AtomW, to handle our internal weight updates. First, the forward pass. We grab a batch of data using our getBatch function and push it through the model. Then we use a cross-entropy loss function to mathematically measure the distance between our model's predictions and the actual target text. Next comes the backward pass. Calling loss.backward computes the gradients across all our parameters, and optimizer.step updates the network's weights to make the next prediction more accurate. Before you loop back around, you must call optimizer.zeroGrad. If you forget this step, PyTorch will add the new gradients to the old ones, accumulating mathematical noise that will derail your training. This graph tracks our model's performance as the loop runs. You can see the loss value starts high, around 4.0, and rapidly drops toward 1.5 as the optimizer steadily aligns the internal weights. This descending line is the numerical proof of learning. It marks the period where the network stops outputting random characters and begins capturing the structural rules of the English language. To pull text out of the model, we build a generate function. This takes our newly trained optimized weights and uses them to run inference. Watch this feedback loop in action. This is an auto-regressive process. The model looks at a sequence, predicts 1 new token, attaches it to the end of the context, and loops it back in as the input for the next step. To pick that next token, we pass the raw model outputs through a softmax function. This converts raw tensor values into a clean probability distribution, allowing us to sample the most likely next character. Text generation is a rapid, iterative sequence of individual, highly calculated micro-predictions. Now we run the script. We feed the model a short starting prompt, and it autonomously generates a structured paragraph directly in the terminal. You have just implemented the fundamental architecture that powers ChatGPT, and you've done it entirely on your own local hardware. The next step is scaling up. Swap your small text file for a massive multi-gigabyte dataset, increase the number of decoder layers, and move the training process over to a dedicated GPU. Modern AI is built on elegant, scalable mathematics that anyone can build from scratch.